Okay, so in this video we're going to be starting topic 7. Topic 7 has 3 different sections in it, and it covers atomic and nuclear physics. Typically we cover 2 of the sections in IB Physics 1, and then we start IB Physics 2 with the last section. And so just to give you an idea about what topic 7 is about, topic 3 was about thermal physics. Topic 7, like I said, is over atomic, nuclear, and particle physics. And so, just to give you an idea of some of the things we're going to be talking about throughout the entire topic 7, we'll be talking about different models of the atom, half-life, and radioactivity. Those 2 we'll be talking about in this first section. The section will be talking about nuclear reactions, different types of nuclear reactions like nuclear fission and fusion, and then how nuclear power plants and weapons work. And then we'll talk more about particle physics and IB physics too. Please remember you can always follow along with this PowerPoint. It's posted on Canvas, and you can always follow along in your IB Physics textbook under Chapter 7. Okay, so this is a very kind of conceptual unit. Every unit has some type of calculations, and so we are going to have to do some type of calculations later on, but not anything too crazy in this unit for the most part. There is a lot of conceptual stuff, like I said. Please make sure that you're taking good notes as we go through this unit, because there's a lot of things that you need to be able to explain, and you need to be able to explain them well and correctly and use the correct terminology. Okay, so definitely take your time as you go through this unit to add the things we're going over to your notes. So the first thing we're going to talk about today is just some very simple stuff related to atomic models. Now, you should already know what atoms are, just from your other science classes. And in thermal physics, we talked about, the general motion of atoms and molecules. We learned that temperature is a measure of the average kinetic energy of atoms or molecules making up an object. We learned that everything, or reviewed the fact that everything is made of atoms. Combinations of atoms are called molecules, and basically everything in the universe that we think of is either made up of atoms or combinations of atoms. And so the idea of the atom comes from, a couple thousand years ago, when philosophers asked the question, if you cut something, like let's say you have like a piece of wood and you cut it in half, you get 2 smaller pieces, and if you cut it again, you get 4 smaller pieces. And the idea was, is there a limit to how small you can cut something? In other words, is there a point where you cut something smaller and smaller and smaller and you get smaller pieces? Can you ever reach a point where you cannot cut anything smaller? And so that's where the idea of the atom comes from. It comes from the Greek word for indivisible, meaning you can't make it any smaller. And so, of course, thousands of years ago, we didn't know that atoms actually existed. It started off, like I said, it's kind of like a philosophical type of question. And so moving on into the 1800s, we start to see chemistry being developed. And a lot of scientists at the time were doing, chemical experiments, and they discovered through lots of different experiments that there were different types of elements, different types of chemical elements. You have hydrogen, you have, chlorine, helium was discovered later on, and so we knew that there were different types of matter. That is, different types of atoms. What we now know is different types of atoms, but we didn't know about the structure of the atom itself. And now it turns out the atom, even though atom means indivisible, it turns out the atom is not indivisible. It can be broken into pieces called subatomic particles, and we'll talk about that later. By the way, atomic means having to do with the atom, in case you could not figure that out. So subatomic meaning smaller than the atom. So the atom is not indivisible, and we'll talk about the pieces of the atom later on. But we didn't know anything about the atom until, going into the late 1800s, early 1900s, when some, higher level experiments were carried out. And so that's kind of what we're going to lead into today. Now the idea is that over time our understanding of these laws of physics have changed, and that's true for any branch of physics. But especially in this unit, I want you to pay attention to how different models of the atoms have evolved over time. Now, there's lots of models we're not going to talk about. Probably the most common one is called the Dalton model of the atom, which is basically that, atoms are little tiny, like, balls, like billiard balls that are, hard and dense, and, they can collide with stuff. Kind of like when we talked about in thermal physics, we talked about, like, the particles in an ideal gas are basically like identical balls that can collide with each other, collide with the container walls. That kind of goes back to the Dalton model of the atom, which is not true, although it was helpful for us in thermal physics. Okay, so the three models we're mainly going to talk about are the Thomson model, the Bohr model, and then later, the Thomson model, the Rutherford model of the atom, and then later on we'll talk about the Bohr model. And so in this video, we're just going to talk about the first two. We're going to start with the Thomson model, and they are in order here, like in terms of when they were discovered, and it is important that you kind of understand how the timeline works. So we're going to start by talking about the Thomson model of the atom. So definitely pause here if you want to add this to your notes. As we go through all of these slides, remember you can always access the PowerPoint through Canvas on your own. As we go through these slides, if you want to take notes, please feel free to pause at any time as we go through. It's important that you take really good notes in this unit because there's so much that you have to be able to explain on the IB exam. It's not as calculation-based as previous units. Okay, so we're going to start with Thomson's plum pudding model. Now, the Thomson model is named after J.J. Thomson, who discovered the electron in the late 1800s. And it's not important that you understand how he discovered the electron, but he was a big deal at the time. Late 1800s, sometime, I think 1897, Thomson did some experiments, and he basically discovered a super, super small particle. Okay, the first particle that was smaller than the atom, which, since atom meant indivisible, you would think that there wouldn't be anything smaller than the atom, but hey, Thomson discovers it. And he becomes a big deal. He actually ends up winning the Nobel Prize in Physics down the road. So good for him. Super famous guy, discovers the electron, super tiny particle, and he discovers that this electron has a negative charge. Now again, the details of how he discovered all of this is not that crucial. Of course, you can look it up if you're so interested. Now, it was known at the time in the late 1800s that most objects are what's called electrically neutral. Now, electrically neutral just means that most objects have an equal amount of positive and negative charge. That's just how it is. Now, that's not always the case, of course. Things can become positively charged or negatively charged. If you've ever, run your feet across the carpet and then shock somebody or shocked yourself when you touch a doorknob, you've experienced yourself becoming charged. And when you touch the metal doorknob, that charge transfers and you become neutral again. And so not everything in the universe is neutral, but most objects are electrically neutral, meaning they have the same amount of positive and negative charge. And so Thomson came up with a model of the atom that had his electrons in them, which he had discovered, of course. And so he came up with a model that suggested that atoms contained electrons held within a soup of positive charge. Now, of course, we now know there's positively charged particles, but Thomson didn't know that at the time. He did know about the electrons, which of course he had discovered, and he knew there had to be some positive charge in there to balance out the negative charge, because again, most objects are neutrally charged, or not neutrally charged, are electrically neutral. And so if everything is made of atoms and everything is, for the most part neutral, then if atoms contain negative electrons, they have to have some positive charge in there somewhere. And since he didn't know about protons or anything like that, he just said they were held within a soup of positive charge. Now, this model of the atom, the Thomson model, is also known as the Plum pudding model. And I'll show you in just a second why it's known as the plum pudding model, but this is basically what it looks like if you want to sketch this. By the way, Thomson does not have a P in it. Sorry about that. But this is basically Thomson's model of the atom, the plum pudding model. In the plum pudding model, we have the atom as a very small sphere, and you have the electrons kind of embedded in the atom, which, again, he knew about the electrons because he was the one that discovered them, and he knew there had to be positive charge in there somewhere. And so This is known as the plum pudding model. Let me pull up a picture of plum pudding. And so plum pudding is a British dessert. You might look at this and not think it's a pudding, but I don't know how they call desserts over there in England. But this is basically pictures of plum pudding. I just went to Google and typed in plum pudding. And you can see if you look at plum pudding, it's kind of cakey. It's not really what we would call a pudding. But if you look, it kind of looks like bread almost. And inside the bread, if you can see there, those are typically raisins or prunes or some type of dried fruit. And so that's where the name plum pudding comes from. And so the idea is in the plum pudding model, if you carry the analogy forward, the raisins in the plum pudding are like the electrons kind of embedded within the atom, and they're kind of sitting in the cakey part or the bready part, which is that positive charge. Because remember, Thomson didn't know that there's actually positively charged particles in the atom. He just saw it was like this soupy type of positively charged thing. And so that's where the plum pudding comes from. Now, the plum pudding model comes from. Now, if you don't like plum pudding because you're not British, which is understandable, then you might want to call it something else. I always like to think of it as kind of like the watermelon model, if you will. And so in that analogy, if you think of like a spherical watermelon, the seeds of the watermelon are like the electrons embedded in the atom, and then they're kind of sitting in the red fleshy part of the watermelon, which would be that positively charged soupy stuff. Okay, so this is Thomson's model of the atom. Now, Thomson, really smart guy, like I said, won the Nobel Prize in physics, discovered the electron, awesome dude. His model of the atom is completely wrong. Well, you know, all models of the atom are wrong to some extent. Some are just more wrong than others. His is correct that there has to be positive charge in there somewhere to balance out the negative charge. It's wrong about the structure of the atom, though. Now, how do we know that? Well, in science, you develop a model, you build like a scientific theory, and then you do experiments to test the model. That's basically how science works. And so along comes this guy named Rutherford, who was a big shot in his own right, Ernest Rutherford. And again, you can pause here if you want to add this to your notes. And basically, Rutherford oversaw an experiment designed to further investigate the structure of the atom. And so Rutherford came along after Thomson came up with his model, not too long, maybe like 5 or 10 years down the line. And he had some people who were working under him named Geiger and Marsden. Now, Geiger, you might have heard of Geiger before. If you've ever heard of a Geiger counter, that's a device used to measure radioactivity. If you've ever seen like a movie where somebody's measuring how radioactive something is, and it's clicking and clacketing, and it's saying something is really radioactive, that's called a Geiger counter. That was invented by Geiger, one of the people who at the time was working for Rutherford. And so this experiment, because it was actually carried out by Geiger and Marsden, the IB calls it the Geiger-Marsden experiment. You might also call it the Rutherford experiment, or see it referred to as Rutherford-Geiger-Marsden experiment, even though Rutherford, I don't know how much of the actual dirty work he did. He kind of got these people working for him to do a lot of the stuff, but he was also involved. He oversaw the experiment. So this is basically how the Geiger-Marsden experiment worked. In this experiment, we shot alpha particles at a very thin sheet of gold foil. Now, it says only a few atoms thick. In real life, we use gold because it's very malleable, and we try to get it as thin as we can. It's not literally only a few atoms thick, but it's as good as we can get gold foil to be. And the idea is we shot alpha particles at a very thin sheet of gold foil with a detector screen surrounding the foil to detect deflected alpha particles. Now, your first question should be, what is an alpha particle? Now, at the time, they didn't know what an alpha particle was. That's why they call it alpha. That's just the first letter in the Greek alphabet, and so they didn't know what it was. They gave it the name alpha. And but they did know that alpha particles were positively charged particles with a very high mass. And these alpha particles were known to be produced by some types of radioactive metals. They didn't know what radioactivity was at the time, but it turns out that some substances like heavy metals emit these alpha particles. And so the idea is if you take a piece of this metal that's emitting these alpha particles in all directions, if you put a sample near the setup, you could project some of the alpha particles towards the gold foil. So this experiment, again, please pause it here if you want to add the sketch to your diagram, basically shows you a very rough outline of how this setup works. This black box represents, something that has radioactive material in it. Of course, the alpha particles don't go in a straight line; they go out in all directions. But you're really only focusing on what's happening inside here. This is the gold foil, again, as thin as we can get it. Gold is used because it's very malleable, and we can get it very, very thin. And then this outside screen in blue is called a phosphorus screen, and it's basically like a detection device. And the idea is that this type of material emits light when it's struck with a charged particle. And so you can literally see a little flash of light everywhere it gets hit by an alpha particle. And so and this means you can kind of figure out what's happening as far as the alpha particles, going through the gold foil or not going through the gold foil. Now, at the time, this was not a fun experiment to do because you literally have to sit in a room and count little flashes of light, sitting in a completely dark room, counting little flashes of light. So this probably was not fun to actually do, but they could use this kind of setup to figure out what the alpha particles were doing when they were projected towards the gold foil. Now here's the prediction they made. Remember, in the Thomson model of the atom that they're testing, the negatively charged electrons are embedded in a positive soup. Okay, something to carry that positive charge. Now electrons are known to be very, very, very small. Alpha particles were known to have a positive charge and be much bigger than electrons. And so the idea was that they made a prediction, because that's how science works, is you design an experiment, you make a prediction. If you assume the Thomson model is correct, here's what their prediction said. They said, okay, these alpha particles are basically all just going to go through the gold foil. I mean, most of the atom is just filled with this kind of weak positive soupy stuff, not anything too crazy. If they hit the electrons are really small anyway, so they're not going to really do anything. Okay, if you imagine thinking shooting BBs into a giant bowl of Jello, even if the Jello has grapes in them, or not even BBs, think shooting bullets into a giant thing of Jello that has grapes embedded in it or fruit embedded in it. I mean, grapes are really small compared to bullets, and they have way less energy. And so, even if there's grapes sitting in the Jello, you would think if I'm shooting a gun into Jello, they're all going to go through the Jello, whether there's grapes in there or not. And so the prediction is you're basically going to see 100% of the little flashes of light directly behind the gold foil. Okay, that is the prediction. Okay, now that's let me show you an animation really quickly. This is basically showing you, this is just a PhET simulation that you can look up on your own if you want. But this is basically the Thomson model of the atom, and those little blue dots represent the electrons, and then all of this in red is basically that positive soupy stuff that Thomson said was in the atom. And this is basically what the prediction was, is these alpha particles are just going to go straight through the atom. Even if we shoot them with really high energy, they're just going to go straight through the atom. We're going to see 100% of the flashes of light on the other side of the gold foil. Okay, and of course the gold foil is made of many more atoms than this. This is just one atom blown up so you can see it. Now this is not actually what we observe. Okay, so this is not the reality. In reality, we see this. The Thomson model predicts that 100% of the alpha particles are going to go straight through. Now, it is true that most of the alpha particles did go straight through the gold foil. More than 99% of the alpha particles went straight through the gold foil and landed back here on the phosphorus screen. But, okay, and this is a very important but, even though it's 99.9%, it's not the same as 100%. Okay, because when they were in there, they noticed every now and again, they would see some flashes of light at very high angles. Like they see a flash of light over here, over here, over here. And that's shocking because that's not at all what should be happening according to the prediction made by the Thomson model. Okay, they should see 100% of the flashes of light behind the screen, and they don't see that. Okay, and so this was shocking. Now here is a quote, and again, pause it here if you need to add this to your notes. But here's a quote from Rutherford. I took this from Wikipedia just to show you how shocking Rutherford found this. It says, when Geiger reported to Rutherford that he had spotted alpha particles being strongly deflected, Rutherford was astounded. In a lecture Rutherford delivered at Cambridge University, he said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. On consideration, I realized that the scattering backward must be the result of a single collision, and when I made calculations, I saw it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute nucleus." Okay, so for the first word we see that term nucleus, or for the first time we see that word nucleus. "It was then that I had the idea of an atom with a minute massive center carrying a charge." Okay, Ernest Rutherford. And so this, again, it was really shocking to Rutherford. Completely disproved the Thomson model of the atom. And remember, Thomson is this really big deal guy, Nobel Prize in physics, super smart. That doesn't mean his model of the atom is correct. Okay, in science, the only thing that matters is experiments and the results of those experiments. Okay, so Thomson's model is disproved as a result of the Geiger-Marsden experiment. Okay. And so if you interpret the results, like if you kind of break it down the way Rutherford did, here's basically the result right here. Very small amount of positively charged alpha particles were deflected backwards at large angles, while most alpha particles, again more than 99% of the alpha particles, passed through and hit the screen directly behind the gold foil. And so if we break this down, what does that mean? What does it mean if only a few alpha particles were deflected? Well, if 99.9% of the alpha particles are deflected, that means whatever they're hitting, because they have to be hitting something, the ones that are deflected, whatever they're hitting has to be very, very small. Okay, now how do we know that? Well, if it was bigger, then more of the alpha particles would be deflected. Okay, so they're hitting something small. Now we know there has to be positive charge in the atom somewhere, and the electrons have the negative charge. Okay, alpha particles have a positive charge, and if alpha particle comes close to another positive charge, they're going to be repelled. Okay, and so that's kind of how the collisions, if you want to call it that, works. In other words, the alpha particles must be colliding with, I use that in air quotes, you can't see me, but it's air quotes, the alpha particles must be colliding with something positive, which makes sense because we know the atoms have to have positive charge in there somewhere. Okay, so we know they're hitting something small and positively charged. Now, if they were hitting something, with very little mass, they would just run over what they were hitting. But they're bouncing backwards. That means they're hitting something heavy. And plus, electrons were known to be, very, very small. So what does that mean about the mass of what they're hitting? Well, it means they're hitting something very heavy, relatively speaking. Now, if you take something very heavy and you make it very small, remember we know that whatever they're hitting has to be small because of this first bullet point, you get something very dense. Okay, and so this is Rutherford's model of the atom right here. This is called a nuclear model of the atom because it has what's called the nucleus. Okay, the nucleus in Rutherford's model is something very small, dense, and positively charged at the center of the atom, and then there's electrons orbiting the nucleus. Again, pause it here if you need to add this to your notes. This video is getting pretty long, so I want to end it here in a second after showing you a picture of the Rutherford model of the atom, but do definitely add all this to your notes. Now, again, this bullet point right here basically tells you what Rutherford's atomic model looks like. You have in the center of the atom the very small positively charged nucleus. That's why this is called a nuclear model, because it is having to do with the nucleus, with electrons orbiting the nucleus. Okay, something like this. Now, We will talk about this later. Rutherford at the time didn't know about protons and neutrons. He just knew it had to be, something positive. The protons and neutrons were discovered later on. Now, Rutherford's model is supported by the Geiger-Morrison experiment. Okay, Rutherford's model of the atom is wrong, but it is less wrong than the Thomson model because it has some piece of evidence supporting it. Okay, now just because you do an experiment and it comes out good for your model doesn't mean that your scientific theory is correct. Okay, you cannot prove anything in science, you can only disprove things. So far, Rutherford's model is supported by the Geiger-Morrison experiment, but it's not proven correct, and actually we'll see down the line, Rutherford's model has a lot of issues with it. Okay, it is definitely not the correct model of the atom, but it's closer than Thomson's model. Okay, so we'll talk more about the Bohr model later in this unit, but notice the evolution, and this is how science works. Notice the evolution in our understanding of atoms and the different models of the atoms that have evolved over time. Okay, each new model built upon the one that came after it. And even our current model of the atom using quantum mechanics, the quantum mechanical model, is not 100% perfect or perfectly understood. Okay, and so that's basically how science works, is we're always building on our understanding of things and using our past models to inform our new models. And so that way we get better and better results as we go through. And so Rutherford's model is wrong, but it's less wrong than the Thomson model, which was less wrong than the Dalton model. Okay, and so that's basically how science works. So please let me know if you have any questions. I know that video was kind of long. I apologize, but please definitely add all of this to your notes and let me know if you have any questions.